All right. So now today we're going to go on and continue our study of antiderivatives. Or we know that we stopped calling them antiderivatives really and started calling them integrals or integration. So someone go ahead and give me a general idea of what an antiderivative is, give or take. You can give me something formal or you can be very informal or you can give me an example. Something about an antiderivative.
Instead of going down, you're going up.
Yeah, more or less. We know that whenever we talked about derivatives, we kind of had this idea that derivatives we were going down a step in the ladder, and then antiderivatives we were going the opposite direction, that is, we're going up. And we're reversing our work with differentiation, essentially. And then also in that previous section about antiderivatives, I also mentioned something like along the lines of calling it an indefinite integral. Primarily because whenever I took the antiderivative or the integral, we always put a special letter at the end. It was plus what? Plus c. And this wasn't an indefinite integral. This told me I just had a family of potential solutions, in other words. It could have been any constant because we know that if I take the derivative of a constant, I get 0. So today we're going to go ahead and look at this. What is a definite integral? Again, I mentioned this a little bit last time, but we didn't really get into it. So these first couple of slides, I actually do not want you to write these down because this is just the theory and the background behind it. I'll tell you whenever it would be a good idea to go ahead and start writing stuff down. Also, another reason that it's going to be very wordy and use some special notation. So let's go ahead and start on talking about the definite integral. Before we actually introduce the definite integral, we actually have to introduce some concepts here and there so that we know what do we need to build up the definite integral. Let's start off with this thing called sigma notation. First off, I want to ask, have any of y'all ever seen this thing called sigma notation? It's okay if you haven't.
I didn't for this notation.
Yeah, so this is my crudely drawn capital sigma letter. So what does this sigma notation mean in math, for example? Well, a sigma represents a summation. That is, I'm adding a group of things, for example. So what does this notation mean? Well, the first off, the way I would read this, top one, this would be the summation from I is equal to m to n of a sub I. And this is going to be am plus 1 plus am plus 2 plus so on and so on. So what does that even mean? What I have down here, I'm going to call that my index, my starting index. In other words, the number that I start plugging in first. So this was I is equal to m. So I start by plugging m into here, and I have am. Then I go up a level, m plus 1 plus m plus 2, all the way up to my final part of my index n. So to help us look at this, I have an example right here. This is the summation of a sub I. What is my starting index here? 1. That means I start off by plugging 1 in for I. If I do that, I get A1. Plus, I go up to A2, and I keep on going up until I reach this top number. So I have A1, A2, and then A3. I reach that top value.
So, for example, if it's not like I negative 1.
Yeah, if it was, say, I is equal to -1, it would be A-1, A0, A1, all the way up to A3. So we have this sigma notation, really big thing that happens a lot. We're not going to focus too much on this. This might primarily so that we can get the proper definition of the definite integral. All right, so we have sigma notation. Now I want to go ahead and introduce, if I timed this correctly, I believe the next one should be a partition. Let's see if I timed it correctly. Partitions. So, first off, we know what a closed interval is, right? If I have from A to B like this means all the numbers from A to B, including A, including B, for example. So let's suppose I have a closed interval where A and B are real numbers. Remember this notation just means that A and B are real. And if I look at this interval A to B, suppose I choose some random group of numbers in between A and B. Like if I had 1 to 2, I would choose a bunch of random numbers of my choice between 1 and 2. And we're going to call that x1, x2, all the way to xn minus 1 inside my interval. And I choose them such that they all fall into this order. A0 is A. A1 is a little bit bigger. A2 is bigger than that. A3 is bigger, so on and so on until I reach the very end. In other words, I order these from least to greatest. Well, if I choose these numbers, x0 to xn, I can call this set P, and I can call it a partition because it takes it and then it splits it up into smaller groups. So, like for example, I told y'all if we had, let's do it, 1 all the way over to 2. Give me some random numbers between 1 and 2, like decimals. What was that? 0.5?
Yeah.
Between 1 and 2?
Oh, sorry, 1.5.
Yeah, 1.5. Let's say I did like 1.3, 1.811. So if I did it like this would be my x0, x1, x2, x3, x4. So I have an interval, and by choosing these random numbers, I split up my big interval into smaller ones. Because I have this interval, I have this one, I have this one, and then I have this last one. So I have 4 intervals, for example. So that's what this is saying in other words. I had an interval, I chose the numbers in between, and then it splits up that big interval into smaller ones. This is what we call a partition of an interval. Particularly, partitions are are interval into smaller intervals. All right, so we have this idea of a partition. So what am I going to do with a partition? Well, I'm going to go ahead and introduce this definition of the related to the partition. So if I'm looking at this partition example that I have here, which one looks like it would be the biggest interval that I'm working with here out of these 4, give or take? This is definitely not the scale, but it looks like the biggest interval would be this one here, 1.5 to 1.811, because that's like 0.311, for example. So y'all just told me that that one's the biggest interval, the widest one, out of those 4. Well, that value, we got it from 1.811 minus 1.5, that's like 0.311, for example. What we actually did there is that we found the norm of that partition. So here I'm introducing this thing called Euclidean norm. I know I'm introducing a lot of notation. This is for all the theory background. If I have a partition P, like what I did earlier with 1 to 2, it's split up into smaller intervals. The norm, which I'm denoting with this P with 2 lines on the left and the right, this is the largest width among all of my sub-intervals. And if I want to use some fancy mathematical notation, here I would say norm is the maximum of the length of my intervals, where those come from the partition that I have chosen. Again, we're not focusing too much on this, just mainly the theory behind it. So we talked about sigma notation, we talked about a partition, and then the norm of the partition. If I want to be exact, technically this is the Euclidean norm, which is, without going too much detail, is the distance between 2 points. All right, so using that definition of sigma, using sigma notation, partition, and Euclidean norm, this is actually going to start to build up. We're a little bit closer to building up what a definite interval is. Let's talk about this thing called a Riemann sum. Again, this is all just background info. Don't worry if it's going right over your head. We're not going to be worried too much about this. So I have a partition of a closed interval. Again, just like if I had that 1 to 2, I split it up into smaller groups. And let's say I have a function f that I can graph, for example. The Riemann sum approximation of f on this interval is given by, I'm going to say this, S sub p is equal to the summation from k equals to 1 to n of f of c sub k of delta times delta x sub k. So what the heck does this even mean? Let's see what this looks like in terms of a picture, for example. So let me move this over to the right so I have space. So let's say I have a function, for example. Let's do it like this, yeah. And label this 1, 2, 3, 4, 5, 6, -1, -2. So let's say I graph a function. I'm not going to specify what type, but let's just say I got a function like this. So here's my function f of x. What I did is that here I have an interval. Let's say I want to work from, I don't know, let's do 0 to 1, 2, 3, 4, 5, 6. Let's do 0 to 6, for example. Again, give me some numbers between 0 and 6 for me. I heard 4, 2, 3. Let's say I focus on those. That means I have one group that's here to here, one that's from here to here, here to here, and then one all the way to 6. So I have 4 sub-intervals, right? So let's read what this is. F of ck, where ck is in this interval for each one of these. So let's say in this first interval, I choose f of ck. Ck is somewhere in here. What is f of ck? That's just a y value, right? Because this is my x values, f of x is whatever's up here. So this one might be here, for example. And then this middle one, we'll say right here. Let's say this one's all the way over here. This little one, let's choose like here. Let's say that those are my f of ck. Those are my y values. The delta xk is how wide are my intervals. So this might be my first delta x. This is my second delta x. This is my third one. This is my fourth one. So looking at this, would you agree that delta x is a width, left to right? Because delta x is how wide is this interval. The f of x is my y value, or we think of y values like heights. So what happens whenever you multiply a height times a width? What's a height times width? Area, right? It's like geometry, we have like a rectangle. Well, actually, that's exactly what's going on here. Delta x is the width. F of ck is a height that I have chosen. That is one of my boxes. F times my delta. And then I can do the same thing for the rest of these, for example. I'm just doing this very arbitrarily. And then we chose this last one like that. So each of these individual boxes that I drew times delta, height times width. And then I add them all together because it's a sigma. So why am I interested in this? Well, if I look at the blocks I shaded, this is roughly the area underneath my curve. Roughly. Not exactly, because we have some error here. Because the area under the curve would be something more like this. I know I'm overshading it. That would be my actual area. But would you agree that the blue boxes, that's sort of in the same ballpark? All right, so this actually gives me the area underneath a curve. Well, this one was a little bit inaccurate. How could I improve my estimate with these boxes? Yeah, because if I have smaller boxes, then I have less empty space, for example. Like, for example, what color haven't I used? Erase all these so that people can see it. If instead I chose really small ones, I could do something like this.
Like really small intervals?
Yeah, really small intervals. And would you agree that one would be probably a better estimate than the one we started off with? That means I made the width of the subinterval smaller and smaller. Now, I'm going to finally tie everything I mentioned here into a definite integral. The formal definition of the definite integral, it looks like a terrible mess. The definite integral is the limit as the norm of the partition goes to 0 of that Riemann summation. And the Riemann summation was this. What is this even telling me? Well, we said that this was my estimate. Those were all the boxes I add together. So this limit is saying, what if I make those boxes tiny, the width smaller and smaller? That's why here we have the partition, the norm of the partition going to 0. That's just saying the width of my boxes gets smaller and smaller. This is just means the norm of the partition. This was from this right here. Again, don't worry about all the fancy stuff. It's just the background so that we know what the formal definition is. We're not actually going to be using this notation, but it's necessary for the background about where did it come from. So this is our definite integral. And when such a limit exists, we actually say that my function is integrable. That is, I can find the integral or the antiderivative. So now we can finally talk about how is the indefinite integral different from the definite integral. Well, the indefinite integral, that was just the antiderivative. One way or another, we can word it a different way, but it was the antiderivative. Based off that picture that I gave y'all, the definite integral of a function gives me the area under the curve. I say quote unquote under because we saw that there was some part that was like the curve went underneath in the negative area.
So I guess it's just the curve, the area of the curve closest to the x-axis.
Yeah, exactly. But then a lot of times you'll hear most people just say the area underneath the curve, depending on how you want to word it. All right, so we have finally defined the definite integral. Now, let's go ahead and do an example of this using a graph. So here I have a graph, and I want you to evaluate these three definite integrals. So I didn't tell you what f is, but I gave you a picture of it. So starting off with part A, this is the part where you can start writing now if you'd like. Part A says, I want the integral from 4 to 8 of this function that I've drawn. Let me move this up so it's perfectly aligned. So if I have a picture, this is really asking what is the area underneath the curve from, well, 4 to 8. So let's go ahead and mark 4 to 8 on this graph. We have 1, 2, 3, 4, all the way to 5, 6, 7, 8. This integral, since we know it represents the area underneath the curve, I'm going to shade what we're looking at. 4 to 8. That's this entire area for part A. I want to figure out what that area is. All right, so how could I possibly get that area, despite the fact that I don't even know what my real function is? Like I don't have like f of x equal to x squared or anything. But what could I do to get that area that I've shaded?
With temp type.
Yeah, we could do some things like that. In fact, for this example, I'm going to claim that we can get the exact area. Looking at this, would you agree that what I've shaded here, this looks like a box and then a half circle?
Yes.
We know how to get area of a box. We know how to get area of a circle. That means I should be able to get this area. And let me shade it this way so that we can specify. Let's call this area 1. Let's call this area 2. All right, so looking at this, can y'all just tell me what the area A1 is going to be, the box?
4 times 1, 4.
Yeah, that's 4. It's 4 wide. It's 1 tall. That's 4 times 1. Area 1 is 4. So I can go ahead and say that this area is 4 plus, oops, before I do that, there is one other thing I'm going to note in a moment. What about A2? What is the area of that half circle? Imagine it was a perfect half circle.
Shoot, I think that might have been pi.
What's area of a circle?
Pi radius.
Yeah. So what's the radius for this one?
1.
1?
Oh, sorry, 2.
2. So area is equal to pi times 2 squared, or 4 pi. What does that mean? What's the area A2 then?
4 times 3.41. So what, like,
Well, not multiplying the pi. We're every number times pi.
oh, so just 4 pi.
Is it 4 pi? Is 4 pi the area of a half circle?
Oh, so 2 pi.
Yeah. Remember, pi r squared is a whole circle. So if I want half the circle, I gotta divide it by 2. So I have 2 pi. I'm gonna erase this. Notice I'm leaving some space here because we are gonna do one thing about this. At 4 and 2 pi. So this is where we had to be a little bit careful. I agree. The area I shaded was 4 for A1, and the area for A2 is 2 pi. One thing I want to note about this area that I've shaded is it above or under the x-axis? Yes. So
negative.
yeah, so both of those areas are negative. That's why I left the space is actually going to be -4 minus 2 pi. So whenever we're doing integrals, we're going to see that whenever I take quote unquote area underneath the x-axis, we're going to call it this idea of negative area because it's underneath. The other way that you justify this is that, yeah, this width is positive, but this length is -1 long. And it might sound a little bit weird and maybe a little bit incorrect for us to be saying negative area, but we're going to use that term for our purposes here. So the integral from 4 to 8 of this function is -4 minus 2 pi. And there's not much I can do to clean that up. So I'm just going to leave that as is. All right, so now let's go ahead and look at part B, the integral from 0 to -4.
That
So
seems super simple.
0 to -4. Before we actually try this problem, is there something odd about the bounds 0 to -4?
It's to the left of the y-axis.
Yeah, how does this compare to the other one, 4 to 8?
I would guess it's going to be similar to the quadrant we were just in. It's also going to be negative.
You're along the right idea. So,
Ooh, we're going to subtract the width is going to be negative, and the height is going to be positive.
well, in this area, I'm gonna have to be careful with my wording here. The first thing I'm gonna put out there, between 4 and 8, which one's the smaller number? 4, definitely, right? So it looks like 4 was a smaller number, and then we went up to the bigger number. How's that comparing to 0 to -4?
So
Yeah, it kind of looks like it's in reverse order. That's a little bit of a problem for us, because usually in an integral, I'm telling you now, is that we usually like having the smaller number on the bottom and the bigger number on top. But what does that mean? Does that mean that I wrote this wrong? Well, not necessarily. It just means I need to be careful about how I evaluate this. And actually, it's a quick fix. I can reverse these bounds by writing this. If I put a negative in front of the integral, I can flip the bounds. So I can write this as -4 to 0 of f of x dx. So this is a rule that I'm honestly glazing over a little bit, but it is an important rule. If I swap the upper and lower bounds, I negate the entire integral.
So it's kind of like making the entire thing negative or so.
Yeah, basically. All right, so now I definitely have smaller number to bigger number. Let's see if I can go ahead and now figure this out. -4 to 0. Well, here's 1, 2, 3, 4, -4 to 0. So if I just want to go ahead and shade that, that's from here. Actually, it's just this box right here.
It's going to be 16.
Wait, is it always gonna be a shape?
Yeah, because this integral is basically area, is how we're going to think about it. So we're always shading it from the x-axis, either up or down to wherever the line is. Last time we shaded down because we went from here to here. Now, since it's above, we go from there to there. All right, so you told me 16, right? Yeah, because it's 4 wide, 4 high, that's 4 times 4. So this tells me I have a negative from here. And this was 16. So we have a -16.
Well, without having to change the integral's notation, if we just remember that if a negative is on top, your answer is going to be negative, could that just be a quick way to do it?
No, not necessarily, because you can have both bounds be negative, and then your answer is positive or negative. The only thing that I was worried about here is that we usually like a smaller number on the bottom. Like, for example, if this was 8 to 4, I would have wanted to swap that too by making the whole thing negative. We usually like having a smaller number on the bottom, because that's how we like to think of numbers. And actually, you're going to hear me say this word, lower bound and upper bound. Usually we think lower bound, smaller number, upper bound, bigger number.
So is it just all depending on how the integral is written?
Yes. Yeah, we're basically being careful about making sure that we're not overlooking it. All right, and then I have this last one. Let's see. I'm gonna move it into the top right corner just so that I don't have to erase anything in case anyone is still copying. C, the integral from -4 to 8. First off, is that in the proper order? The smaller number on the bottom, bigger number on top? Yeah, for sure. So if I want the area from -4 to 8, I'm going to clear up some room here from the first part A. So the area from -4 to 8, that would be from -4, this as well, this little triangle piece here, and everything that was here. So this entire blue region, because it's from -4 to +8. So that means I have to get the area of all of these shapes. Well, we've already done a good bit of the work already, because we know this right here, I wanted it to be here. This was already 16. We did that in part B. We already did this part too. That was -4 minus 2 pi. So if I want to finish this up, I just need these two triangles, whatever they might be. So now I'm going to ask, do we know how to get area of a triangle?
1/2 base times height.
Yeah, we know that for a triangle, area is 1/2 base times height. So it looks like I have two triangles here, a bigger one and then a smaller one. Let's start with the bigger one. What's the area for this triangle?
What? 8? 6?
Yes, so this is 3 times 4, we get 12. 12 times 1/2, we get 6. What about the smaller triangle right here?
1/2.
Yeah, we get 1/2 because it's 1 times 1 times 1/2. So now I can add all of these together. 16 plus 6, I get 22. 22, let me write it out so that we don't mix our numbers up. 16 plus 6 plus 1/2, so that's these three shapes, plus -4 and -2 pi. So adding all of those together, 16 plus 6, I get 22. 22 minus 4, I get 18. 18 plus 1/2, I believe we get 37 over 2, minus 2 pi. So I just combined the plain numbers and I left the pi alone because there's no real good way to combine a number with adding it to a pi. So this is our visual idea of a definite integral. We have this here. Any questions about what I did in this example one?
Oh, wait, hold on.
Yes.
Isn't that supposed to be negative?
Oh, is it supposed to? Oh, yes, you're right. I missed that myself. That's supposed to be a -1/2 because it's down there on the bottom. So that should be -1/2. That does change my answer slightly.
30.
Yeah, 35. Good catch. As you can see, very easy to make a mistake whenever we're going through these real quick. So we had one big benefit here. I gave you the graph, and the graph were basic geometric shapes. We know how to get area of a square, a triangle, a circle. So
The Goldilocks version, yes.
what was that?
Is this like the Goldilocks version?
Yes, this is like everything is perfect. We don't have to do that much work. So what if I had, and you don't have to write this, this is going to be what if. What if I had a graph that was more like this. Let me draw my X and Y. Um, and assume that these aren't perfect half circles either. I intentionally made these very little wonky and crooked. The question is, how would I even do that? And let's say that I knew what this function was. I don't know, it was some kind of weird x function. In other words, if I only gave you the equation and it doesn't turn out to be these perfect little shapes, how do we even find the area? Well, this is where we actually have to go back to that idea that I showed you at the beginning. We can get an estimate of this area if we wanted to. We're not going to actually do it. Again, if I wanted to, I can get a bunch of rectangles, and it would give me some good idea of this. Being a little lazy with drawing the rectangles. That would give us a pretty good estimate of the area up to a certain point. But I'm going to claim that what we're going to do on Monday
It's very much more accurate.
is we're going to have to figure out how to get that exactly. Not even an estimate, the exact number, what that is. And it's going to involve, there's a reason why we use the same notation for the integral here and the antiderivative. To get that exact value, we are actually going to use the antiderivative. And that's actually why we use the same notation. It's not like we use one for area and then one for antiderivative. They are directly related to each other. We're going to use the antiderivative to get the exact area, as we'll see.
Of the function or just the integral area?
The integral of the function is the area. Because remember, we did it right here. The integral is the area.
So the derivative of the integral is the area. Antiderivative. Essentially.
The derivative of the integral is what?
The area.
Not the area. The integral is the area.
No. I was saying the antiderivative of the integral.
The antiderivative of the integral. I think we're mixing up antiderivative and integral. We got all these fancy long words. Long story short, the definite integral is the area underneath the curve. And actually, what we're going to do on Monday is I highly recommend that you do not miss class on Monday, because we're going to cover something called the fundamental theorem of calculus. And it's going to be, it's again, one of the major things that I'm almost certain you'll be using for almost the entirety of Cal 2. So I do not recommend missing class on Monday. All right, besides that, that is all for today. I'll see y'all on Monday. Have a good weekend. If you have any questions, please let me know as per usual. Again, also, please register for classes. I know I say it all the time, but please do so.